Let's solve this differential equation. We can just integrate on both sides. In the left-hand side, the integral of the derivative is the function itself. In the right-hand side, we can integrate the terms separately. The power of x will increase by 1. The constant 3 will stay there. To compensate for the power what increased, we will divide by that. The integral function of the exponential function is itself. We might have to add some constant. Let's solve this differential equation. We just need to integrate on both sides. How can we integrate the natural logarithm? From some book of tables, you can find that the integral is x times ln x minus x. Let's check this. If we differentiate x times ln x minus x, the derivative of x is 1. Then we are using the derivative of the product here. We have x times the derivative of ln. Derivative of ln is 1 over x. This gives 1. Okay, and then last we have the derivative of x, which is 1. This 1 and this 1 will cancel out, and we just have ln x. Because the derivative of this is ln x, the integral of ln x is that function. Maybe need to add some constants there. Well, then the second thing, how can we integrate the tangent function? Tangent is sine of x divided by cosine of x. Let's add there a minus sign. Now, if we call cosine of x the function f, in the numerator we have the derivative of f. So we are integrating a quotient of a function divided by, derivative divided by the function itself. This will give the logarithm of that function, and perhaps plus some constant. So we will have ln of cosine of x. Now we have the integral of the natural logarithm and the integral of the tangent, and we can use these facts to find the solution. Let's see. In the left hand side we get that the integral of the derivative is y, and we can substitute our integrals here. We have x times ln x minus x, and then minus ln of cosine of x, and maybe some constant. Here is the solution. Let's solve this differential equation. It's enough to integrate on both sides. The integral of the derivative of y is y. In the right hand side, we can recognize that if we have some function f here, its derivative would be minus sine of x. Let's add here two minus signs. In that case, this will be the derivative of the function. So we are integrating derivative of our inner function times e to power that function. This gives e to power that function plus some constant. You can check this by differentiating. If you differentiate this, you will get this by the composed function differentiation rule. So our integral is minus e to power cosine of x plus some constant. And this is our solution. Y is equal to this function. Let's solve this differential equation. It's enough to integrate on both sides. In the left we get y, and in the right you learned how to integrate these kind of things in the first week or in the previous course perhaps. If you check some book of tables, you can find that the integral is 4 to power x divided by the natural logarithm of 4. Well, how to think about this? If we have some b to power x and we integrate, the integration formula is of this form. If we have the special case e, then the formula gives this one. But now ln of e to power 1 is just 1, and we get the familiar result that the integral of the exponential is the exponential. Okay, so we just had to integrate. Here we were a little bit thinking that how the integral was done. Let's solve this differential equation by integrating on both sides. We want to integrate a square root. Let's express the square root as a power. We have t to power 2 plus 16 to power 1/2. Now inside the square root we have a function. Maybe we call it g of x. If g of x is t squared plus 16, then the derivative of g would be 2t plus 0, that is 2t. Okay, so it seems that we have the derivative of g here. If we also denote that f of x is the square root of x or x to power 1/2, then the left hand side takes the form we have the derivative of g times f at g of x. Perhaps this seems familiar. This is the derivative of the composed function. Okay, now if we take the equation and we integrate on both sides, we will get that y is equal to the integral of this one. Well, integrating this one, the derivative will vanish. So we will just get f. Okay. Sorry, there was a problem. Not so easy. Not so easy because in the formula there is a derivative here. Okay, let's think again. Okay, now we are ready to integrate. If we would integrate x to power 1/2, we would get that the power would increase by 1, and we would compensate here so that if we differentiate, then these terms would vanish. Okay, so that seems okay. Now we are integrating a similar kind of thing, but we have some function to power 1/2 times the derivative of the function. The formulas of the previous course give that the integral is the function g to power 3/2 times 2/3 plus some constant. So 2/3 times t squared plus 16 to power 3/2. That's the result. In the next equation we have that the derivative of y is equal to y. Can you remember any function so that the derivative of the function is the function itself? Well, these are very famous formula in the differentiation rules. We have that the derivative of e to power x is e to power x. And even if we add some constant here, we have that the derivative of a constant times e to power x is the same function. It follows that y is equal to this function. If we don't notice this result, then how can we get the result? Well, let's start from here. This separable equation we can divide by y. Y derivative divided by y is 1. We need to integrate on both sides. In the right hand side we get x plus some constant. Now how to integrate the left hand side? If we would integrate 1/x, the integral would be ln x. Well, and actually here, let's see, ln absolute value of x. Okay. So we have that ln of absolute value of y is equal to this. Let's take both sides and put them to the exponential. E and ln cancel out. Here we can use some formula of the exponentials. like this. Now, this constant here is always positive, but now that we have the absolute value of y here, we can think in that way that let's forget about the absolute value and say that this constant here can be anything. It can be some capital A. Okay, we got the same solution. Let's solve the equation. Derivative of y is y over x. We can divide by y to obtain that y prime over y is 1 over x. We can then integrate on both sides. The integral of 1 over x is ln x plus a constant. Similarly in the left, we get ln y. Well, we might have to add absolute values here. Let's take the exponential on both sides. Let's use some rule of exponentials in the right hand side. Now we can cancel out these exponentials and logarithms, and we will get that absolute value of y is absolute value of x times some positive constant. Well, we can forget the absolute values and get that y is some constant times x. We can check the answer by substituting. If y of x is constant times x, the derivative of y is that constant, and that seems to be a times x divided by x, that is y divided by x. The equation is satisfied.